Hello, today's topic is locality, or how do you find the data when you have a collection of databases. The contents of our distributed database is a collection of documents which we call roll-ons, and interconnections between these roll-ons as well. And we are operating under a constraint that most actions are executed by a single transaction, and a transaction does not span multiple databases, so we're not doing distributed transactions. The worst case scenario, in some situations we have to update several databases, and the way we do that is by an assured sequence, so that we register a sequence of actions to be completed, and then we begin processing that sequence, and we delete that sequence only after all the transactions have been processed. So if there is a failure, then on restart we re-execute the sequence if there's still this pending sequence to be performed. So it's not atomic, but it's assured, and these transactions, of course, would be restricted to a limited set of transactions which are repeatable. Okay, so we've got going to have a lot of small databases all tied together. You can probably have more than one on the same computer. We're looking at maybe an upper limit of 500 databases networked together using UDP, and more on that in another video. So that gives you a lot of points of failure. So the way we do that is by having pairs of databases, which are hopefully not on the same computer. That would be a misconfiguration. So we would have an active database and a hot backup for each node in the distributed database. Now, how do you find the data? Every roll-on has a home database where it resides, and in addition to participate in different relationships, there can be secondary roll-ons. So a primary roll-on resides on the roll-on's home database, and secondary roll-ons can reside anywhere it is needed to support a relationship. So, for example, the documents are organized in a bush structure with a single root node, which we call the arc. And this means that our structure is built out of parent-child relationships. We put the relationship, we co-locate the relationship with a home roll-on of each child. This is important because a child can have more than one parent, and when we get into semantic processing, it's important to be able to order these parents, and to be able to order the parents, we have to have the complete list of parents on a single node. So it seems a little counterintuitive, but it works for us. So when you create a relationship between two roll-ons, a parent-child relationship, for example, the parent-child relationship is specified on the home database where the primary child roll-on resides. So you can operate on that there. The problem, of course, is when you want to see all the children of a particular database, of a particular roll-on. This then requires determining where the children might reside and sending a query out to all of these databases, and then processing the sequence of responses to collect a sorted list of the children of a given roll-on. So it involves parallel activity, so it's not as slow as it might be. Okay, so here we go. Let's do a little picture. So we've got, let's say, a pair of systems, a pair of arcs, or databases, a pair of databases Now, and then there's the interconnections. When we talk about UDP, we'll address the scalability issues relating to these connections. Now, how do you know the home roll-on of how do you know the home database of a given roll-on? Well, every roll-on has a unique identifier, which is a UUID postfixed by the name of the database. So that makes it easy. If once you have the ID, you can locate the roll-on. What we do is we partition the roll-ons by type. So every roll-on also has a type, and the complete name of a roll-on is the type. It's a two-tuple of the type and the extended UUID. Now, that presumes that all the roll-ons of a given type will fit on a single database, and we don't make that presumption. So we have two different kinds of database. We have manager databases and we have repository databases. So, and we just identify these by their name. So let's say, for example, we have a user database which is the manager for all of the user roll-ons. And then it might have two repositories associated with it. So the idea then is that we can identify the repositories based on their name, because the repository names are prefixed by the name of the manager. So when you're creating a new roll-on, the creation process involves the manager database, which then determines which repository the user roll-on will reside on. So given the type of a roll-on, you know where it might be. In the case of a user, it could be on either of the repositories or possibly on the manager. For any given relationship, we know the types of, for a given parent, we know the type of its children. For a given child, we know the types of its parents. Typing is not quite simple. We allow multiple inheritance. So if you're looking for where the child roll-ons of a given parent roll-on are located, you have to determine all the different subtypes for that child type, and then do the query on all the databases where it might reside. Where each type, as I said, is always associated with a specific manager. So it's quite an extensible system. It's probably overkill, but if you're going to tackle all the issues of scalability, why stop short of a completely scalable system? Thank you.